So welcome back to the Calculus Analytic Geometry. What we have been doing so far in our last discussion, basically we talked about in very detail about definite integral, that how to compute the definite integral by definition, what do the definite integral mean, and then we also talked about the indefinite integrals actually. And we saw that actually that indefinite integrals are nothing more than the antiderivatives actually. So what we are going to do today, so in today's discussion, we will like to interpret the definite and indefinite integrals in more concrete terms and more in a physical way actually. Okay, so let's just start with, for example, indefinite integral. Let's start with indefinite integrals. So the indefinite integral is integral of this form, f(x) dx. So what does the indefinite integral is essentially telling us? It's when you are, for example, computing an indefinite integral, what you are looking for. You are looking for a function, some function f of x, f capital X, where the f capital X can be treated as the antiderivative of the function f of x actually. Okay? So in other words, when we are solving an indefinite integral, you are trying to answer a simple question, that this given function is the derivative of which function. Can you find a function? Can you propose a function? Can you suggest a function, say f, to which if I differentiate, I get, what do you call this, small f of x. In other words, this is a precise description of what you call antiderivative that we have seen previously. So the antiderivative, so when you are solving an indefinite integral, what you are basically asking is that what is the antiderivative of this function? And the antiderivative of this function is going to be basically a family of function. And what is the relationship between this and this? Since this f is the antiderivative, so you're going to say that f prime of x is really equal to what you call f of x. That this f of x is indeed a function whose derivative is this integrand or this small f of x function actually. So this is it, what you call is the basic essence of computing the indefinite integrals and integrals in general actually. So no matter what kind of integrals you are solving, you are basically trying to answer this question that, if you have been given this function is the derivative of which function? In other words, what is the antiderivative of it actually? Okay? And if you have this basic essence, of idea in your head, you will always, you will never get astray, and you will even I would say that this basic table of integrals would make sense to you actually. That this basic integral of integrals would make sense to you. That why the antiderivative of x power n is x power n plus 1 over n plus 1. Okay? It is just because that if you differentiate this, this x power n plus 1 divided by n plus 1, then you're going to precisely get what you call x power n actually. So if you differentiate it, you're going to get n plus 1 times x power n plus 1 minus 1, everything divided by n plus 1, and you recover what you call x power n. So you will not, so usually, what people do, the kids do, during their calculus, they just memorize this actually. Okay, so they don't have a justification in their head that why the integral of x power n is x power n plus 1 over n plus 1 actually. It is just because this is the function to which if you differentiate you're going to get x power n. Why the integral of sine x is cos x or minus cos x? You can see it. I know that derivative of cos x, okay, derivative of cos x is negative sine x, okay, is really negative sine x. But when you are solving this integral, you are asking for a function whose derivative is sine x, not negative sine x actually. So what you can do, so instead of say computing the derivative of cos x, let's compute the derivative of minus cos x actually. And when you're going to compute the derivative of minus cos x, you're going to see that you're going to get minus sine x, and this would be really the sine x actually. So this makes sense that why the integral of sine x is negative cos x, because the derivative of negative cos x is sine x. Simple. Why the integral of 1 over x is log x, because the derivative of log x is what do you call 1 over x. Why the integral of 1 over 1 plus x square is tangent inverse x, because the derivative of tangent inverse x is this 1 over 1 plus x square. So in other words, when you are trying to solve an indefinite integral, you are basically trying to answer the situation, answer the question that okay, which function or this given function is the antiderivative of what actually. Okay? So this is what really is the basic idea behind the antiderivative, and you have to always keep this in mind. No matter what integral you are solving, this is what you are doing. Then in our last discussion, we also talked about indefinite integral. Okay? The integral of f of x dx from a to b. So we saw it's one of the interpretation that okay, say if f of x is this curve, say it is defined on an interval a to b, split the interval into subintervals, okay, create the rectangles, okay, and add the areas of these rectangles, that is going to approximate the area of what do you call area under this given curve f of x. So when you are computing this integral, what actually you are saying that I want to compute the area under the graph of f of x between a to b, okay, between a to b. So this is what is the common interpretation of it actually. But we will in today's discussion we will basically learn several techniques for solving such integrals, but in few moments we will start having discussion on various interpretations of this guy actually. Okay, maybe computing the area under the curve does not seem too much interesting to you, but when you will treat f as some physical quantity, you will see that the integral, the definite integral, has what you call beautiful meanings. Definite integrals. So the integrals with limits. If you remember, something that is going to be very helpful in making the different kind of interpretations of definite integral is the fundamental theorem of calculus. So if you remember the fundamental theorem of calculus, it says that if you have a function that is continuous on a to b, okay, in other words, it is a continuous line segment, curve segment, okay, that is defined on an interval a to b, there is no gap in it, then the integral of f a to b, this f of x dx can be easily computed. So this function gives you a recipe to compute such integrals, pretty quickly. Because in our last discussion we kind of discussed pretty kind of a cumbersome ways, pretty complicated way of computing the integrals, actually, definite integrals. But this tells you a very easy recipe. So what is the recipe? The recipe is that compute the antiderivative of this small f of x. Say the antiderivative of the small f of x is this capital F of x. And then evaluate this the antiderivative from the limit a to b. And this evaluation is going to be f of b minus f of a. So this is statement that integral from f of x dx, where f of x is continuous over the interval a to b, is equal to f of b minus f of a, where this f is the antiderivative of a to b. This statement is called the fundamental theorem of calculus. Okay, fundamental theorem of calculus. So it gives you a good recipe for computing such definite integrals. We will do several examples today. Okay, so for example, if you have to compute from 0 to 1, say x square plus or maybe x square minus 2x dx. Okay, so what does this theorem is telling you? Since this guy is a polynomial, so it's a continuous over 0 to 1, so there is no trouble in it. So this fundamental theorem of calculus tells you that compute the antiderivative of it. We know that the antiderivative of it is going to be x cubed minus 3 minus 2x squared by 2, so it's going to be x squared from 0 to 1. And then substitute the limits. So first you're going to put the above limit, the final limit, okay, and there is reason for it actually, we will see in a minute, minus 1 square, and then substitute the lower limit, which is going to be 0 minus 0. So really this integral is 1/3 minus 1, and this is going to be negative 2/3 actually. So this is what is the value of the definite integral. Okay. So this makes your life easy. But now using the fundamental theorem of calculus and the fact that f prime of x is an what do you call so f of x or the derivative of capital F of x is this small f of x. In other words, that f of x is indeed an antiderivative of small f of x. Using this notion and this, let's see a very interesting kind of interpretation of fundamental theorem of calculus and hence definite integrals. Now I know that this statement is true, and I know that my f of x is basically f prime of x. So I can substitute on the place of this integral. So f prime of x dx, if you integrate this from a to b, you're going to get f of b minus f of a. Okay? Now what does this statement is telling you in its current form? So the f prime of x is representing what? So f prime of x is, okay, it's the rate at which f is changing, where f could be your some favorite physical quantity. Okay, so rate at which f is changing due to the fact that x is changing, when x is changing. Okay, that's what it means. So this is representing the changes in the function f, where f is some physical quantity, okay, the small changes, tiny changes. What does this integral is representing? Okay, so the integral, we have seen it by definition of what do you call definite integral. That integral is basically an stretched s. It's the sum actually. So you may interpret now this statement as that the sum of all tiny changes in f, sum of all tiny changes in f from A to B is equal to the net change in f actually. The net change in f from A to B actually. So if you combine all tiny changes in f from A to B, you're going to end up with the net change in f from A to B. Okay, where A is the initial point and B is the final point actually. And let's see that, okay, that's one interpretation of it. And let's see that now, using this, what kind of interesting, conclusions you can get actually, or what kind of interesting statements you can deduce from this statement. So for example, you woke up in the morning, okay, and you saw that there is a certain temperature, your mobile phone is showing. So imagine that you woke up in the morning and your mobile phone is showing, say, 22 centigrade. Okay, that the temperature outside is 22 centigrade. And say after some hours, maybe say in afternoon, you again check the temperature and your phone is showing a temperature of, say, for example, 37 degrees centigrade. I know that within this time period, so imagine this is 7 a.m. and this is really, say, 2 p.m. Okay? So, in the morning it was 27 centigrade, in the afternoon it became what you call 37 centigrade, for example. Now, I know that between this time period, the temperature must have changed. Okay? So, if this is 7 a.m., this is time axis, and say this is temperature axis, and this is, say, for example, 2 p.m. Okay. At 7 p.m., so the temperature is 22 centigrade. Okay, somewhere here, and at, say, 2 p.m., it's say 37 centigrade, so it's somewhere here. Okay. So now in this time period, the temperature is not going to be static actually. This kind of gives an evidence that temperature has changed, and how the temperature can change actually in the given time period. Sometimes it can go up and sometimes it can go down. Okay, so imagine that at 7 p.m. you woke up, at 8 p.m. Cloud came and it rained, so the temperature went down, and then after some time sun appears and the temperature goes up again. So temperature could be really a function of this kind actually. Okay, so it's gonna be a function of this kind, that in which the temperature is constantly going up and down. Okay, so it is changing actually, and so it's not gonna go smoothly. It's gonna constantly go up and down and reach to, for example, 37 centigrade. So what does the fundamental theorem of calculus is telling you? The fundamental theorem of calculus is telling you that if you keep track of, or if you put together all changes in temperature, okay, all changes in temperature, okay, so if you sum up, so if you sum all changes in temperature, okay, say from 7 a.m. to 2 p.m. or whatever, okay, you can call it 7 to say 14. So if you see it on the 24-hour clock, so it's going to be 7 to 14. So if you sum up all changes in temperature between 7 o'clock to 14 o'clock, okay, then, and this T is, say for example, smooth, the temperature is changing but smoothly, then the fundamental theorem of calculus is saying that sum of all changes in temperature from 7 p.m. to 14 p.m. is going to be the temperature, the net change in temperature. And what would be the net change in temperature? Temperature at 14 o'clock minus temperature at 7 o'clock. So initial temperature, final temperature minus initial temperature. So if you sum up all temperatures between these two instants, then the sum of all changes in temperatures is going to give you the net change in temperature, okay, from 14 o'clock to 7 o'clock actually. Okay. So this tells you a beautiful story. So this makes sense. You can say, we can talk about some more examples. For example, we talked about, so we kind of saw the different applications of what do you call different applications of the derivative. So imagine this is representing, so this cylinder or this huge tank is representing the tank of water in your building actually. Okay? So you have building and this tank representing, is the tank of water in your building. Okay? Now we know that, usually what we do, so, we keep on, for example, we kind of run the motor, okay, water motor, and, the water falls in, okay, through the pipes, and the water level in this kind of increases actually. So imagine if it is really low in the morning, okay, you run the motor, the temperature level, the volume of the water, okay, it goes up, okay, and then for example you use, so it's like this water tank is being constantly used, so you constantly pour the water and you constantly take out the water by using through the taps and using in the kitchen and so on and so forth. So this water level constantly goes up and down, okay, the water level constantly goes up and down, the volume of the water in this tank goes up and down all the time actually. So imagine at the instant t1, okay, so there is instant t1, you observed that the volume of the water in the instant t1 was, say, v of t1. Say v is representing the volume of the water. Okay, so v is representing the volume of water at time instant t. Then v of t1 is going to represent the volume of the water at instant t1. And then what can happen, that okay, we kind of kept on using this water and pouring new water into the tank, okay, adding new water into the tank, and say after some moments t2, some hours, you checked again the water level in the tank and it turns out to be v of 2. Okay, v of 2. So these are your two observations, that at t1 you checked water level was v of t1 and at t2 you check water level, v of t2. Fundamental theorem of calculus is telling you that, by the way, what would be the interpretation of v prime of t now? The interpretation of v prime of t is going to be the change in the volume of the water, okay, when the time is changing actually. So this is the rate at which the volume of the water is changing. So if you, for example, compute or sum up all the changes in the water from the instant t1 to t2, okay, from the instant t1 to t2, then, okay, so what this statement will, so this statement is meaning this is the sum of all tiny changes in the volume of the water that is happening due to the different reason, adding the water, using the water between the instant t1 and t2. Okay, so if this adding and subtracting of water, okay, and using of water from the tank has been, say, constantly done actually, so it's kind of a continuous function, then the fundamental theorem of calculus is going to tell you that this sum of all changes in the volume of water is going to be equal to the net change in volume of the water actually. So in other words, it's going to be V of T2 minus V of T1. And now you can see another interpretation of the definite integrals. And these interpretations are different from the area under curve interpretation. Okay? So if you take your f, okay, in the integral as some physical quantity, you can interpret this in many, for example, different ways. Let me give you some more ways. So in our discussion over the application of derivatives, we talked about, for example, the mass and the density of a rod. So imagine this is a rod, okay, which is not homogeneous. So it is made up of, say, different kind of materials, or the level or the quantity of mass, and say even it could be homogeneous, doesn't matter actually. Then if I define, for example, m of x as the mass, so if x is some location on the rod, then m of x is representing, say, the mass of the rod from, okay, so from left to the position x, from the left end point to point x on the rod. So m of x is representing the mass of all rod of this, segment of the rod actually. And say rho of x represents the density of rod, okay, at x, or up to x. Okay. So rho of x kind of represents the density. Density of the rod at x. Then what is the relationship between rho and m? So we have talked about it, that the rho is basically dm of x by dx. Okay. Now, if I say that I want to sum all densities, okay, depending on x, from a location on the rod A, so let's A is this location and B is this location on the rod. So I want to sum all densities of the points from the location A to the location B dx. Okay. So now this definite integral is representing what? Sum of the all values of the densities at x from the point A to the point B. Then what would be this sum actually? The sum of all densities, since the density is the change in mass, okay, at the location x, then this is same as summing up all changes in masses from the location A to the location B. Then what would be this? By fundamental theorem of calculus, this would be equal to the mass up to the point B. So from the mass up to the point B, if you subtract the mass up to the point A, so what is going to remain is this mass actually, the net change in mass, the net mass of the rod from the segment, from the point A to the point B on rod. So this is going to be m of B minus m of A actually. right? So it's m of b from the m of b to m of a. Okay. So this is, another interpretation. Let's think about the interpretation from the perspective of, say, rectilinear motion.